Hi, good afternoon, everyone. Welcome to the session on the Porous media. My name is Miguel Nóbrega. I'm a professor at the University of Minho in Portugal, and I'll be the chair of the session. We'll have 4 presentations, and the first one will be given by Dr. Norbert Weber, and is entitled Open Source PM Fuel Cell Model Combining the Unsaturated Flow Theory for Porous Media with Springle's Model. Please, Norbert, the floor is yours.
Thank you very much. I will try to share my screen. One moment, please. Can you see it now?
Yes, we can. Thank you.
Perfect. Thank you. Yeah, what I will present was basically some work which was done in cooperation between Dresden, the Research Center in Jülich, and the EMAT in Madrid. So what I will present is basically about modeling of polymer electrolyte fuel cells. As the name already says or tells us, such fuel cells consist of polymer electrolyte membrane, which separates the 2 electrodes, which you can see here in the middle. And each of the electrodes consists of a porous media, as well as 2 flow channels, which supply oxygen and hydrogen to the fuel cell. And then this hydrogen can only cross only the hydrogen ions basically can cross the electrolyte layer and react then to water, which is transported out of the cell with the airflow. And the water can also diffuse to the other side of the fuel cell through this membrane. Modeling the cell voltage is basically very easy for such a fuel cell because the open circuit potential is well known, is described by a simple formula. The only thing what is missing is computing the over voltages, so the voltage losses, which appear in the fuel cell, so this red colored area here in the polarization curve. And how does it work? Basically, we have 3 different over potentials which might appear. The first one is the ohmic over potential, for example, in the electrolyte layer, but this includes also, for example, contact resistances between different layers. The second important thing is activation. So the activation over potential means basically when you ionize the oxygen or the hydrogen, you lose a certain potential, and this needs to be included here in the model. And finally, we have also mass transfer losses, with what means here is that the cell might accumulate, for example, a lot of liquid water that in the end the oxygen and hydrogen does not reach the reaction zone anymore. These 3 things are not so difficult to compute, but depending on the state or on the operation, on the current density, the values of these 3 overpotentials can change dramatically. So depending whether the cell is wet or very dry, the ohmic overpotential or the mass transfer losses can be the major contribution. When you now want to compute these 3 losses for the fuel cell, you do not need only to know the water content. You also need things like the gas velocity, the pressure. You need to know how much water is inside the membrane. You need to compute the conductivity. You need phase change between liquid, water, vapor, the mass fraction of the various species. And this means in the end that this is quite complex because all these equations are very much coupled. One quite challenging thing is 2-phase modeling. And basically for fuel cells, 3 different 2-phase models are used. So in the most simple case, people use the so-called multi-phase mixture model, especially with Fluent. And they say that they compute only one intermediate, or let's say one mean velocity of the liquid water and the gas phase. This is simple, this is easy, but not so accurate. The most accurate approach would be to use an Euler-Euler model for the 2-phase modeling, which means then solving the Navier-Stokes equation separately for the gas phase and the liquid water, and coupling these 2 velocities by some special terms. I didn't do any of these twos. I used some kind of intermediate model, which is called the unsaturated flow theory. And this means basically I solve the Navier-Stokes equations for the gas only and solve some diffusion-like transport equation for liquid water. And this transport equation is derived from porous media theory. So this means it holds only, or it's only correct in the porous electrodes, but not in the gas channels. Here you see basically all the equations which need to be solved. And as you can imagine, this is extremely complex, and not only because these are many equations, but because they are tightly coupled. So if you imagine that at some point in the fuel cell, some water evaporates, this will cool then locally the cell, this will change there the conductivity, will change the current density, and will basically influence all these equations. So it's in the end really difficult to get such models to converge. The model which I presented you is, in general, I would name it an engineering model, which means it includes quite a lot of simplifications, but it is possible to model a complete cell or even a complete stack. And I think the most important limitations is the liquid water transport, which I told you already. So the equation holds only for the porous media, but it does not include the liquid water transport in the channels. Secondly, it is a steady state model, so no time dependence. And lastly, the spatial resolution is somehow limited. So let's say the fuel cell is maybe 10 centimeters long, but the catalyst layer is maybe only 10 micrometers thick. And these very thin or very small things I was not able to resolve. So there are some limitations, I would say. Yeah, modeling such a fuel cell, I use several measures, so as done by Professor Biel already in the past, which means I have a global mesh for the complete fuel cell where I solve, for example, for the temperature. And secondly, I have then an electrolyte mesh where I solve for electrochemistry. And of course, then I need to map, for example, the current density between these two meshes. Yeah, and lastly, I have also two separate meshes for the air and the fuel, where I solve for the velocity, for the species transport, and so on. Now I would like to show you two examples, two real cells, which I simulated with this model. The first one you can see here. It was operated at the research center in Jülich and used basically pure air and hydrogen at a temperature of 70 degrees. And here in these images, you can see a few results. When you look, for example, on the top right, you see the liquid water content here in black and in red. And you can see when the air enters the fuel cell, the air is still quite dry, but when it goes out on the bottom, you see how it gets red and how the water content increases. Or when you look on the temperature on the top in the middle, you see also that below of the channels, we have always a slightly higher temperature, simply because there the reaction rate is higher, the current density is higher, so we also get higher temperature due to the reaction. With that, I would like to come to a second example. This cell here was operated at CIEMAT in Madrid and is quite similar, but here they used oxygen instead of air to operate the cell, and the fuel channels are a little bit different. As you can see on the bottom, they are bent on the sides. And here again, I would like to show you a few results. You can see here on the sides and on the bottom that there we see where the channels for the air and fuel, where they are bent, the liquid water, for example, accumulates. Also, the current density is smaller in these areas. It goes down to 0. And we can see also in the white gray image on the bottom on the right that there the oxygen mass fraction goes to 0 simply because the diffusion wave from the channels is too long so that the oxygen does not reach these areas. This model cannot model everything. It needs quite a lot of input data. For example, the exchange current density, the kinetics and so on, these are values which need to be fitted still from existing polarization curves. And the reason is simply that such a fuel cell changes its properties with aging, and including all these aging effects would require also to have much more detailed membrane models or catalyst layer models, what would be extremely complicating. Anyway, in the end, I tried to reproduce these measured polarization curves for both cells, and you can see it here that fits quite well. With that, I would like to come to the end. Basically, if you would like to use, or if you would like to do fuel cell modeling, there are two codes which I can recommend. The first one is OpenFuel, which was originally developed for solid oxide fuel cells, is now available also for high temperature PEM fuel cells, and is now also improved to work with low temperature PEM cells. And I think it will be published very soon. And this model there will use an Euler-Euler approach, so it should give quite accurate results, and you can find it here at the link presented on the top. Yeah, and the thing what I presented today, you can download and test it as well, and I included also the two examples which I presented here today. Yeah, with that, I'm at the end, and I would like to thank you for your attention.
Thank you, Norbert, for your presentation. So we have time for questions now. It seems there are no questions from the audience, but we have one. The problem you presented is obviously a complex system to be solved. Many coupled equations, and you mentioned some convergence problems. Can you share any advice to deal with those, with the problem? Any recommendations for persons that are interested in dealing with the same problems? How should they handle it in order to have reach convergence to any methodology that you propose to do it?
What I did was basically, after solving each equation, let's say oxygen mass fraction, I always did a check. I checked for all cells whether the oxygen mass fraction goes below 0 or whether it goes above 1. And if this happened, the solver throws some kind of warning. And this is important because we have so many equations and the solver usually explodes at some point, but then you need to go back from this explosion and to find out at which equation it diverged first. And there's these warnings helped quite a lot. This is one thing what is important. And the second thing was sometimes limiting certain values, for example, limiting the current density to be only positive. I think these are the two most important things to do. And I think there are other possibilities there, but there I would need to look in my notes.
Okay. But thank you anyway for the recommendations. So we have already questions from the audience. One from Kaspars. How can these very complex models be validated in all details with experimental measurements? Do we envisage if that's possible? Because, okay, we're dealing with a complex system, and any recommendations for experimental assessment?
I think one good way would be neutron imaging, because with neutron imaging you can see very well the water distribution or the liquid water distribution inside the cell. Maybe also with synchrotron, but I'm less sure. And then I would say also that experimentally with a potentiostat you could measure, for example, the local current density, local cell voltage and such things. But I didn't try that honestly.
Okay. Another question from Lionel. Would it be complex to include VOF model in the multi-physics framework of your fuel cells?
The answer is yes.
It's
I'm not sure how to do volume of fluid in porous media. Probably that's possible, but you would need an extremely fine resolution. It would make sense to couple it to do the volume of fluid only in the channels and to do something else in the porous media. But also this coupling would be very complex. I have no idea, honestly, how to do it.
Okay.
I'm sorry.
Okay, thank you. And the final questions. The final question is from Jega. Have you tried single phase modeling for the PM fuel cell model?
Maybe I tried it in the beginning because the solid oxide fuel cell model is single phase, no? Because it operates at very high temperatures. There is no liquid water. But in the end, yeah, the interesting thing was really to do it two-phase. So I spent most of the time in two-phase modeling. Okay.
So thank you. Thank you very much for the presentation, for the questions. We need to advance with the session. And the second presentation will be given by Mr. Rajan Kumar Shanmugazudaran. Hopefully I pronounce it correctly. And the title of Rajan's presentation is Numerical Modeling of Liquefaction Around Marine Structures. Please, Rajan, please advance. We're not seeing the slides, nor your voice. I don't know.
I guess you can see my screen now?
Yes, yes,
yeah.
Perfect.
Also, you can hear me, yeah.
Yes, thank you.
Yeah. Okay, welcome everyone. My name is Ranjit Kumar Shanmugasundaram. Yeah, I'm currently working in Wiki in Germany and also pursuing PhD at TU Braunschweig, Germany. In this presentation, I would like to share my work, Numerical Modeling of Liquefaction Around Marine Structures. This presentation actually is a part of NewLimos project, which is Numerical Modeling of Liquefaction Around Marine Structures, which is like same as the title. And yeah, this is actually the link for our project. And also you can see look at the different project partners down here. The main objective of this project is to develop an open source solver in OpenFOAM to solve for liquefaction around marine structures. This project also comprises of small-scale experiments at one of our project partners in Poland and large-scale tests at GWK Hannover. These tests capture liquefaction, which fills us the knowledge gap, and also it is helpful to validate our numerical toolbox. At the right is the ultimate design that we would like to validate at the end, which is actually designed by one of our project partners, Keycon. This basically consists of a gravity anchor mounted on a seabed, which is then connected to a floating structure and a wind turbine with the help of ropes. These ropes exerts pressure on the gravity anchor, which influences for the seabed liquefaction. So what is seabed liquefaction? If you look into sea, we have the soil particles on the bottom and waves on the top. These soil particles always have shear stress between them, which helps to withstand load. For example, this gravity anchor or the structure. These waves on the top increases pore water pressure, which is the pressure due to water inside pores of the soil grains. This reduces shear stress and the soil grains loses its capability to withstand load. Soil then behaves like a highly viscous fluid, which is liquefied soil. So for liquefaction, actually there are two types. One is residual liquefaction and momentary liquefaction. Residual liquefaction occurs mostly in case of progressive waves, where we have the periodic pressure variations in the seabed. due to this, like we have an alternate compression and alternate expansion and compression, which changes the shear stresses in the soil. These shear stress and shear deformation would gradually rearrange the soil grains. And later, this pressure of the water increases inside the pores. So in order to liquefy, this pore pressure should exceed the initial effective stress. And when you look into momentary liquefaction, this occurs mainly during the passage of wave trough. In unsaturated soil, the pressure gradients are really large. These larger pressure gradients allows to generate lift in the top layer of the soil under wave trough. So and this momentary liquefaction occurs if this lift exceeds the submerged weight of soil. And this liquefaction occurs only for a short period of time. In order to model this numerically, we have 3 different regions to be solved. One, the waves on the top, which we represent in terms of wave equation. Second one, the soil region. Since we cannot treat each soil particles individually, we treat this as poroelastic solid with an incompressible pore fluid. And finally, the liquefied region. We do not have this liquefied region at the beginning. So it is then treated as a once the soil region gets liquefied, we treat this liquefied region with a different set of equations. We are right now at very beginning of the project. So in this presentation, I would like to share my results only till onset of liquefaction. Also in the cases that I'm going to show, I just have the waves and I don't have this effect of this gravity anchor. So there are actually 3 different formulations. One is quasi-steady, in which we have the acceleration of soil skeleton and the acceleration of pore water pressure relative to soil skeleton and are ignored. And in the partial dynamic, in which we have the acceleration of soil skeleton, and fully dynamic, we have both the acceleration of soil skeleton and the acceleration of pore water pressure relative to soil skeleton are considered. So in this presentation, we are actually trying to do in terms of quasi-steady approach. For that, we have this bio equations, in which we have the 2 different equations. One for equilibrium of poroelastic soil. So to solve for equilibrium, we have the stresses in each direction should go to 0. At the left-hand side term is the stress-strain relation, is actually due to the stress-strain relationship of the elastic material, and the right-hand side term is due to the normal pore water pressure in the normal direction. And second is pore fluid continuity. For the pore fluid continuity, we have the Laplacian of this pressure is dependent on this volumes change due to the compressibility effect and the volume change due to the changes of the soil skeleton. And so this epsilon represents actually the volumetric strain, and 1/q represents the compressibility effects. So in order to validate this, we have 2 different cases. The first case study, we have just the waves on the top. This actually, I verified the journal from Xu and Eng's. Okay, for that, I actually considered the model with traction-free displacement and the waves on the top, cyclic boundaries on the sides, and then 0 displacement and 0 pressure gradient at the bottom. These are actually the properties that I've used to validate the model. For that, I had used water depth of 20 meter, wave height 6 meter, time period 10 seconds, and wavelength of 122 meters. And seabed properties that I had used was soil depth of 50 meter, Poisson ratio 1/3, porosity 0.3, degree of saturation 0.975, and modulus as 26 million. So here I have the results for the pore water pressure plotted against the seabed depth. For that, I can see that we have the results actually very close to the analytical results. The solver that I have used was actually an older one, which I had just modified it. The solvers that I had used was geotech foam, and then this biofoam. But for this case, we don't have this pore pressure buildup. As I actually told earlier, we have for the pore pressure to build up, we need rearrangement of soil grains. For that, we have this wonderful equation from Sumo. Here, this P represents period averaged pore water pressure. And also we have this source term, which contributes for the pore pressure buildup. This source term is equal to the ratio of initial effective stress to the number of cycles for liquefaction times the time period. This number of cycles for liquefaction is actually dependent on the amplitude of shear stress and initial effective stress. These alpha and beta are some empirical coefficients, which are actually the functions of relative density of the soil. For this liquefaction criteria, we have that the period average pore water pressure, when this period average pore water pressure exceeds this initial effective stress, we have the soil region completely liquefied. So in order to validate this, we have another example from Sumo, which shows the onset of liquefaction. For that, we just have to add an additional boundary condition for the period average pore water pressure. Here, the wave properties that I had used does not differ a lot, but I had a relatively small soil depth. So this is actually the novel step in our project. We have extended the earlier biofoam with an implementation of the pore pressure buildup equation. You can see actually from the results for the liquefaction criteria plotted against the seabed depth. As the time progresses, you can see the liquefaction criteria increases, and after 15 minutes, you can see the top part of the soil completely liquefied. And also these results were close to the analytical solution. So as a conclusion, I would like to say that in this work, we have implemented the bioequations and the pore pressure buildup equation, which shows a very good occurrence with the analytical results. And the next step in our project is to study the effect of seabed response to a rocker plate. So in that case, we would have instead of waves, a rocker plate with an oscillating boundary. Then we would extend this for the installation of foundation anchor. And then we would have this anchor with different degrees of freedom. Finally, we would compare the results with the large scale and small scale experimental results. Thank you for your attention.
Thank you, Rajan, for the nice presentation. So we have time for 1 or 2 questions now. It seems there are still no questions from the audience, but I have one. You presented and you compared the results of the solver you extended with analytical solutions and you mentioned that it's quite difficult to have analytical solutions for the problem you have. Have you considered using other methods like the method of manufactured solutions to enlarge the validation of the problem you are trying to solve?
Right now, like we are just like we have already have some analytical results and we are just trying to validate it. And probably in the future, will have some results from the experiment, results from large scale and small scale experimental results. And that is actually the main goal of our project, to validate our numerical toolbox.
I agree, obviously, you need to, at the end, to validate with numerical, with experimental results. But my recommendation was somewhere in between the very simplified analytical solutions you can have, and maybe using like the method of manufactured solutions to further access the solvers you have. It's obvious. It's a recommendation. Sometimes it's useful when we don't have enough analytical solutions to assess the system, because at the end, when you are comparing with experimental results, you are also validating the representability of the model, and sometimes you solve correctly the equations, but the equations might not be the appropriate ones or at least the models might not be the appropriate ones to solve the problem. But it's obviously a recommendation. It's not.
Yeah, yes, I agree.
I don't know in detail the problem you are trying to solve in order to have additional recommendations.
Yeah.
Mm-hmm. Okay. So it seems there are no questions from the audience. So we'll advance with the session. Thank you,
yeah,
Rajan,
thank you
for your presentation. The next talk will be given by Mr. Dennis Meyer, and is entitled Porous Mechanical Foam, a Toolbox extension for flow deformation analysis in variably saturated porous media. Please, Dennis.
Yeah, thank you, Mr. Nobrega. Let's see, let me share my screen. It should be shared now.
Yes, it is. We can see it.
Okay, perfect. So I'm happy to present to you today Porous Mechanical Foam, which is a toolbox for the analysis of fluid structure and soil interaction. And it also can handle variably saturated porous media. I'm working for the German Federal Waterways Engineering and Research Institute. So as the name suggests, we're interested in all the materials that are present in our waterways. The hydraulic engineers, for example, they're really interested in the fluid, of course, in the surface water, and in the interaction between the surface water and our hydraulic structures. And there's already a really good tool to do that. It's called Solids for Foam. And there are a lot of good tools in here. But there is one thing missing in the picture, and that is the material that our river beds and the embankments are made out of. And that's the porous material that's called soil. And to model this one, you need at the hydromechanical coupling that we just heard from in the last presentation as well. And another thing that's really important is the unsaturated and saturated mechanics that go on, because we have different or varying water levels and groundwater levels. So all of this is a poromechanical foam that we started to develop to be compiled on top of Solids for Foam. So just to extend the things that you can do with Solids for Foam and have a complete fluid structure soil interaction analysis. So what is Solids for Foam in detail? For one, we have a new solid model that is that incorporates the hydromechanical coupling. And with this, you can use all the material models for the mechanical part that are already present in Solids for Foam, but we also included 2 new ones that are better suited for soils in particular. Also, we bring unsaturated mechanics to Solids for Foam, which includes the capillarity effects above the groundwater table and the effects of gas entrapments, which alter the compressibility of the pore space. And of course, you need some boundary conditions, because we have this notion of effective and total stresses in porous media, and there are some boundary conditions that needed to be implemented as well. So we have the poroelasticity as the backbone of poromechanical foam, and we included the term for the change of saturation here. And so we have the mass balance of pore water and the momentum balance of the solid matrix with the change of the saturation. And we also, of course, need initial and boundary conditions for the 2 primary variables. And these 2 equations are coupled with one another by the soil deformation and the pore water pressure. When you have processes like excavation, for example, as you can see in this picture here, you always have varying levels of saturation, and it varies with time and with space. And these varying levels of saturation alter the behavior of the porous material quite a lot. So when you're far below the groundwater table, you have the saturated zone, which where there's really only water in the pore space, and you can view the water as incompressible. However, if you're getting closer to the groundwater table, you start the likelihood of there being like entrapped gas bubbles inside the pore space becomes quite high, and so the saturation becomes a function of pressure. When you're above the groundwater table, the water is mainly held in the pore space by means of capillary action, since the pressure falls below atmospheric pressure. And this is typically described by a curve called water retention curve, which is just a functional relationship between saturation and pressure, where I have the section here, which is just the negative pressure, or the pressure that's lower than atmospheric pressure. To show you what poromechanical foam can do, I have 3 verification tests here, one for the full saturated zone, one for quasi-saturated conditions, and one for the unsaturated zone, even though this one is more like a combination of all the 3. For the saturated zone, I have the Mann-Cry effect here, which is a fully saturated porous ball. And I only have 1/8 of the ball here because of symmetry reasons, and then we can look at the inside of the ball, of course. And the ball is loaded with a constant pressure from the outside, and the water can drain freely to the outside surface as well. And when you look at the pore pressures in the center of the ball, then you notice that with time it increases until it hits about 1.2 times the loading that was applied from the outside, which is a poromechanical effect, and only happens in this with a poromechanical material. And after you hit that maxima, you start to have a rapid drawdown of the pore pressure, because the water finally finds its way out of the ball completely. So we have the analytic solution and the solution of the calculations, and they agree quite well. So we're really confident that we have the coupling right. So we next looked at the quasi-saturated zone, where you have the soil the gas bubbles in the soil, and we have a 1D column here, which is loaded with a hydraulic load. That means we have a water column on top of the soil column, and the water table is changing periodically. So what we're doing is we're looking at 3 different points in the soil: the top, in the middle, and in the bottom. And when you have around 10% gas in your soil or in the pore space, then you see that you get this dampening of the outer loading, and also you get a phase shift. And when you reduce the gas content to around 5%, then the dampening gets lower, and the phase shift is also smaller. The last but not least, is the unsaturated zone, which is probably the most complex to analyze, because you have a lot of nonlinearities in here. So we have this 1D column that is halfway filled, halfway saturated with water, and above the groundwater table we have this saturation distribution according to the water retention curve. We're now giving a mechanical load on the top of this column, and we increase it linearly and then hold it constant for a while. What will happen is that the pore pressure, or the water table, will rise, in this case to around 25% of the initial height. And when we hold the loading constant, the water table will drop again and will slowly approach its new value. So we have the pore pressure generation in the saturated zones, which push the water table upwards. And when we hold the loading constant, then we only have the dissipation of pore pressure into the unsaturated zone, which drops the water table, and then it slowly distributes the saturation according to the water retention curve. So why are we doing all of this? Why do we bother with unsaturated mechanics? I have one really nice example from engineering practice here, which is this coastal protection structure that is loaded with the tidal loads from the North Sea. So we have this tidal water level changes. And when you look at a slice through the structure, what you see is that you have this chamber here, which is which can be cut off or it can be closed off with these two gates. We have a concrete slab down here, which makes up the foundation of the structure. And underneath the concrete slab, we have a sand layer and then a clay layer. The sand layer is encapsulated by two sheet pile walls, one to the left and one to the right. And then the pore pressure responses to the tidal loadings are measured in this sand box here. And the interesting part here is that we only see pore pressure amplitudes of around 30% of the loading from the outside of the tidal water level fluctuations, which we only really could explain with entrapped gas in the sand layer. So what we did is we made a simple 2D plane strain model with 5% gas in the pore space. And we included some more of the region in front and behind the coastal structure, and gave the tidal heads as hydraulic loads on the soil interfaces and as total stresses on the concrete slab. And what you can see is that for such a simple 2D model, we could recreate the fluctuations in the pore pressure quite well. And so I think we have good evidence that there must be some gas in the pore space down here that we can, so we can calculate it with this assumption. And there are also a lot of other phenomena going on here, but due to the time restrictions, I cannot go into detail too much. But all the other zones that we looked at, all the other time frames that we looked at, we could also manage to model quite well. So what are the key points that I want you to take home today is that there is a extension to solids foam which enables it to have the fluid structure soil interactions, and then this toolbox can also handle variably saturated poromechanics. The code will be made available in fall this year sometime, and yeah, that's it from my side. So thank you for your attention, and I'm happy to hear questions.
Thank you, Dennis, for the presentation. So we have already a question from the audience. Don't you believe local thermal non-equilibrium conditions could affect the model?
Can you repeat it? Sorry, I didn't.
Don't you believe local thermal non-equilibrium conditions could affect the model? I believe it's
thermal
non-equilibrium conditions. Yes.
Yeah, thermal conditions. It could be, but I don't think that in this case there would be, or because in our cases there would be too much thermal variation. So I don't think that there would be.
Yeah, it's and to provide you more details, they affect the water density, retention, flow, other processes. These thermal effects. But,
I know, but I think in most cases and in most engineering cases for our embankments and our structures, earth structures, there is not too much of a difference in the thermal or in the temperature, but it could be. I have to look into it actually. Not too much.
Okay, very nice. So I believe there will be no more questions, and we are in fact on time to move to the next talk. Thank you, Dennis, again for the presentation and for the questions. And the last talk from the session will be given by Dr. Lionel Gamet, and is entitled Triperiodic Fixed Beds of Spherical Particles. Please, Lionel.
Thank you, Miguel. I hope you can hear me and see my screen.
We can hear you. We're not seeing your screen yet, but.
Oh, okay. So why can't I share my screen? Share.
Yeah. Now we can. Thank you.
Okay. Presentation mode. And I will come back to the title. Thank you. And so I will talk to you about triperiodic fixed beds of spherical particles. So this is a work done by Florencia Falkenov, who is a PhD student at our group. The work is done in collaboration with Romain Volk and Michael Bourgoin at the École Normale Supérieure de Lyon in Lyon. And they do there with Florencia experiments on these fixed beds, but I will not present you any results of the experiment today. We have also the contribution of Nicolas Pinzi, who's a trainee now working at IFPN and doing some job on these fixed beds too. So just an outline, which is rather classical: introduction, numerical methods, results, and conclusion. Just one word about who we are. IFP Énergies Nouvelles, we are a public research center and also a training institute involved historically, I would say, in responsible oil and gas, but more and more into renewable energies, which is also including biofuels, green chemistry, and all those things. Also sustainable mobility, which is for the transport sector. And we have a new goal in our group, which is to get involved into climate, environment, and circular economy. In that field, you will see things like polymer recycling, for instance. So the group is 1,600 people, and the industrial group in over is 45,000 people, with about 1 billion turnover euro. So the problem of the energy storage is when you have intermittent energy, like for instance wind turbines, you want to store the energy when it is produced for a future use. So you have the problem of storing and the solution. What are the solutions for storing this energy? So we are currently developing a process which we call advanced adiabatic compressed air energy storage, which means simply that during the compression of air that you use for storing the energy, you will keep the heat released during the compression in a fixed bed, which is just a porous media. You can see it like a porous media. You will keep the heat for future release and future discharge when you use your stored energy for, let's say, regenerate some electricity, for instance. So we need in that thing for understanding and fundamental description of what's going on inside a mixed exchanger consisting of a fixed bed of particles. And in reality, the fixed bed will be made of stones. So in porous media, you have pore scale effects that can affect the integral scale of the medium. So this is an image taken from wood, paper of wood. What's going on at the local scale can affect what you can see at a level above. So we will. So this is not yet implemented, but the objective is to compute volume averaging theory. So if you take Navier-Stokes equations, both momentum and also an energy equation, and you average them over a representative triperiodic volume, then you get this kind of equation where you have terms that you need to close if you want to have models for this. And the closure of these terms, I will not get into the details of what are all those terms, are done by doing direct numerical simulations over representative periodic volumes. So what are the numerical methods we've used? I've just here recycled an old slide I had about this problem. Well, we'll do a CAD, which is coming either from a DEM code, which we call Cran3D. This is an in-house code at IFBN. And then from this CAD, we generate a grid with classical block mesh and snapping hex mesh workflow, with just handling a little bit carefully what's going on edges when you have edges. So here we have spherical particles, but the particles are not always spherical. They could be cylinders, and also when you are dealing with periodic volumes, you could have cuts of the spherical particles by the frontiers of the cyclic boundaries. And then we run DNS codes with simple FOAM-based methods. Basically, we also have some extensions of based on simple FOAM. So for the cyclic, you have to be careful of what you are doing, in particular on the pressure boundary condition. I will come back to that on this slide. So what we do when we have, let's say, a cubic multi-periodic volume, we first apply in step one a cyclic AMI boundary condition with a source term, which is based on the either a patch mean velocity force function in OpenFOAM, or you also have mean velocity force. These source terms, what they do, they just impose inside your domain a pressure gradient such that you verify an imposed and prescribed velocity, either on the patch for patch mean velocity force, or on the volume for mean velocity force. So out of there, we get the pressure gradient. And then, in order to be comparable with other softwares and literature, we are doing a second step, which is just removing the source term and applying the pressure jump of the step one to the boundary conditions, and with something that is called fixed jump AMI boundary condition. So this is a sort of modified cyclic AMI, but this is included in the standard sources of OpenFOAM. Let's discuss a little bit about results and what we have obtained. We have first validated the workflow on simple cubic, which is just one sphere inside the cube, and face center qubit arrangements. So the second one is consisting of one sphere spread over the 8 corners of the cubic domain, and half a sphere on all the face centers of the cubic domain. So you get in total the equivalent of 4 spheres of volume in this case. And in the case of the FCC, so you have edges going on, and I mean arising from the intersection of the spheres with all the faces of the cube, which you need to capture. This is done with the eMesh files in OpenFOAM and more details into Snappy. And you have here some visualization of the grid. You can see that on the right-hand side, the cyclic AMI patches are quite well matched. So on the simple cubic arrangement, when we compare the force that exerted by the fluid over the solid, I mean, all force, I mean, viscous plus pressure, either when you vary the solid void fraction on the left, or where you vary the Reynolds number on the right at a constant solid fraction for the second, and at a constant Reynolds for the first one, we get a fairly good comparison with literature data. For instance, with Zik et al. The literature, when we vary the solid volume fraction, and you see here in the small graph, you have the error, which is less than a few percent. Same thing for the FCC arrangement. When we compare the overall force, in that case, I only have the epsilon is varied, so I have a constant Reynolds number, and I have here also a very good agreement against the literature. Well, it's an old paper, but anyway, these data are still solid. We have performed then over validation on a periodic and random fixed bed made this time of cylinders. So we have here a 16 array of 16 cylinders array that is made with DEM solver Grand 3D. For those who want to go a little bit further, Grand 3D is also coupled with the Pelligrip solver. You have here the website. And this Pelligrip solver is able to solve DEM with dynamics computed by Grand 3D. So here we have all, of course, edge capturing necessary, and in particular on the edges of the cylinders and also on the intersections of the cylinders with the boundary cyclic conditions. Just a bit of colorful dynamics. We have here velocity, pressure, streamlines inside this bed. I will not insist too much on that. And we'll go directly to the validation data that we have obtained. So this is a comparison of the overall force, so viscous again and pressure together on each of the cylinders. So you have here 16 cylinders on the x-axis, and on the vertical axis you have the difference, I mean in percentage, of the force between OpenFOAM and Pelligrip solver. And we are here again in a fairly good agreement with this solver, which is nice for us. Just one remark: in this case, the solid volume fraction is about 4.2, so 20%. Then we did a bit of the same thing on fixed beds of spheres this time, and you have here on a fixed bed of about 10 spheres. More spheres are in preparation, by the way. We have here a comparison of the overall force on each of the sphere, and you have here again a fairly good agreement within a few percent of the difference between the forces obtained by OpenFOAM and obtained by Pelligrip. On this case, we have a volume fraction of solids about 1/3. Let's go down to the conclusions and future work. So I've shown you simulations of three periodic arrangements that were validated on order of packings and also on fixed bed made of cylinders and spheres, and we have a very good agreement on the forces comparisons. We will now apply that to more complex beds and more dense beds too, with maybe some issues on meshing in particular. And the ongoing work is going to focus on heat transfer. Of course, that's the objective of the project AACAAS, to get with the heat transfer volume average theory and also closure model that we could use for dimensioning the process. And on long term, there is also some future work that will be done more oriented toward multiphysics. I mean, the applications are not actually the same because they are going to be more into heterogeneous catalysis applications. So gas liquid flow with mass transfer between the phases. That will require maybe some specific handling of the wall boundary conditions, of the gas liquid boundary conditions in particular, because these catalyst grains are mostly made by a very porous media. So that's going to be one question. Of course, there will be some porous media simulations inside the catalyst particles and reactive flow simulations, because most of the heterogeneous catalysis are made for reactive applications. I thank you for your attention and welcome any question, if any.
Thank you, Lionel, for the nice presentation. So we have time now for some questions. We still don't have any questions from the audience, but I can start. Okay, we have one. Why use grains 3D as opposed to workflow developed by Bocardo in your institution, which uses Blender to create the packing?
Yeah, there is different ways of doing DEM. I mean, Grand 3D is able to handle very complex shapes of particles. which maybe is not the case with Blender. I don't really know the workflow done by Blender. This was done also because with Grandtrade, also because historically the first method that was developed at IFPN for DM was Grandtrade. And Grandtrade is also coupled with the solver Pellegriff, which I presented here. I mean, I presented some results of Pellegriff, which were done with the Grandtrade to coupling.
Okay, thank you. For me, it was not really clear because from the images I'm not familiarized with the problem. But are the particles touching each other? They are in contact in the model.
They can be. They can be. I mean, not in the present cases that I showed here, because the volume fraction is rather low. I mean, you have 50%, etc. But when you have a fixed bed of spheres, in that case, they are not touching either. Also, you can have, when you reach about the packing limit of about 0.6, which is about 60%, 63%, then yes, you can get particles touching, which creates a lot of problems for meshing. In particular, snappy hex mesh might not like the gaps, the small gaps that you get in these domains, in these regions. And also the cases here that we did for the force validations were made on purpose, not touching. Why? Because in that case, the force that you get out of OpenFOAM is really physical and can be compared with the Pellegriff and Grandtrade solvers. If you have particles touching, then you can have bridges in the mesh. And if you have bridges in the mesh, then you have some parts of the particles that are missing, and then the force might be wrong.
Yeah, understand. Yeah, then my question would be the mesh, but you already answered that.
Okay,
so, thank you. No, it's I understand. It's it was a difficulty I was envisaging, but okay, you are aware of that, and very nice.
You can cope with it with the parameter gap level increment that you have in Snappy. You can impose it at two different places in the dictionary, either as a global parameter or as a local parameter for each geometrical part that you want to mesh. Let's say you have a geometrical part that has small gaps, then you can impose here a gap level increment, which is incrementing the level of refinement locally when you meet a gap, when Snappy meets a gap.
Okay, perfect. So I believe there are no more questions. So this is the end of the session. Thank you very much, everyone, for attending this session. Thank you for the speakers, and looking forward to see you soon in other places. Thank you. Bye-bye.
Thank you.